Hello everyone. This video is a quick proof to show you the magnitude uh, in uniform circular motion. The, the magnitude of the centripetal acceleration is equal to the velocity squared divided by r. Okay, this video is just quick proof. Okay, so we want to find the acceleration vector, the magnitude of acceleration vector. So the first thing we need to know we need to find out what's the acceleration vector. Okay, we need to find it out. And acceleration vector, we all we know is right now is it's the derivative of velocity vector with respect to t. Okay, so it's a so and now so what's our velocity vector? Do we have information for velocity vector? Let's assume we have a point P here. Okay, a point object is doing uniform circular motion and now it reached a point P. Okay, this point it has the velocity. Okay, but actually, what I just said, I often in uniform circular motion, the velocity we just magnitude of a velocity. Okay, magnitude of velocity vector, we call it velocity. Okay, so so for this information, okay, let me draw another assistant line here. Okay, so we have a velocity here. So can we write down the velocity vector? Can we do that? We have magnitude of velocity v, and the point P here is theta with respect to the horizontal axis, counterclockwise. Can we do that? Can we write down the acceleration vector? Okay, so let me decompose. Okay, so now we have to decompose this vector. Okay, we have to compose to x component and y component. So that means it should be here. It's x component and y component. So you want to decompose the velocity, the magnitude of velocity in the xy coordinate. I think the theta, you need a geometry information. So here is theta. So here's theta. So here is theta is also here. So here is also theta. Okay. So by this information, we decompose this velocity into two components. So the x direction is x direction. Be careful. It's minus v sine theta. It's minus sign because it points to the left direction. So under this coordinate, the left is negative. Okay, and for the y, it's v. Yeah, be careful. It's v cosine theta positive. V cosine theta. Okay, so that's very good. That's very good. Okay, so we finally write down our velocity vector. Okay, now we have to do the derivative of v with respect to t. Okay, derivative of v with respect to t. So, and previously I just say if you want to do derivative of a vector, you just do doing the derivative in each component. Okay, so for this problem, do the derivative x component, do the derivative of y component. Can we get the answer? So let's see. Okay, since the negative and negative v is a constant, we see in the uniform circular motion, the magnitude of velocity is the same. So we can factor out and decide theta over dt. Right now, this is a problem. Okay, this sine theta over dt, because it is doing a uniform circular motion, so the theta is function of time. Theta is function of time. So the same thing, the sine theta also function of time. Sine theta also function of time. So how could we make this derivative? Okay. We have to find out another information to doing this derivative, because doing direct derivative, it is possible to do that, but let's need more math. So I don't want to put too much math in there. So let us find something else. Can we do this? Can we find other information to solve this out? So the problem, we need to find something to substitute the sine theta and the cosine theta. Okay, what's the sine theta from this geometry? Sine theta is r over, we can say it's because the position is here. Let's say this is yp. Okay, putting a y component. Yeah, in Cartesian coordinate, it is xp. Okay, we transform the sine theta to r over yp, and cosine theta transform to r over xp. Okay, then we put this information back into our derivative. So our derivative velocity with respect to time. So we will have the let's say minus v and r over yp and dt I plus d v times rxp dt j. Okay, so is this information helpful? Yeah, if you're smart and you think it's helpful, because v and r is also constant, because in uniform circular motion r is also a constant, and like I said, uniform circular motion velocity is also a constant. The magnitude doesn't change. So we can factor this out, and the position, the y component of position plus our v xp component position x component derivative, doing derivative on x. And so what's this term? This just vy. This just vx. Don't you see that? Yeah, you see that? It's just velocity in y component. Yeah, the position makes the derivative with time is velocity, right? And it's y component. So it's y. It's y component. So this is x component. So it's vy and vx. And do we have information for vy and vx at the beginning? Yeah, at the beginning we already said. Okay, this is vy. This this vx. This always vy. We already have this. Okay, so we can put this information back to here. So vy is v cosine theta and vx minus v sine theta. So what we will have minus v is v cosine theta, right? Cosine theta. I plus our v is let me check. V cosine minus v sine theta. Okay, minus v sine theta j. Okay, so we finally get out. It's much easier. So we have r minus v squared cosine theta I plus r over minus v squared sine theta j. Okay, this is the acceleration, centripetal acceleration vector. This is the centripetal acceleration vector. But right now, what we want to do, we want to calculate the magnitude of the centripetal acceleration vector. So you just put this in, just square sum, and you will find at the beginning looks very ugly, but after all, you will find it just equal to r v squared over r, not just what you see in textbooks. Okay, the magnitude of acceleration vector, centripetal acceleration vector, is v squared over r. Okay, so that's the quick proof for this magnitude of centripetal acceleration. I hope you can understand it. And okay, this is the video. See you in the other video. Bye bye.